I'm going to talk about knowledge-aware natural language understanding. This is work done at Carnegie Mellon University and here, and it's joint work with Waleed, Matt, Jayant, Chris, Luke, and Ed, who's my advisor. Okay, so the goal of natural language understanding is to encode human utterances and reason about them. Encoding typically involves extracting low-level features like part-of-speech information or named entity features or things like that if you're building a feature-rich model. Or more recently, people have been learning high-dimensional representations for encoding utterances as well. When you're reasoning, you're doing some sort of a task-specific prediction, if you're, for example, building a system to recognize textual entailment, you're predicting whether a given utterance entails another utterance, or if you're doing sentiment analysis, you're predicting what kinds of sentiment is conveyed by the given utterance, and so on. Given this observation, we can define a natural language understanding system succinctly using the following two equations, where you first encode the given utterances and produce some sort of encoded representations. And given that encoded representations, you then apply the reason function to get the final task-specific predictions. The question we ask in this talk is whether this is enough. Let's see what's missing. Say, for example, your language understanding system is encoding the following two sentences. She ate spaghetti with butter and she ate spaghetti with chopsticks. A good language understanding system needs to identify that the phrases with butter and with chopsticks are performing two different functions. Concretely, if you're building a dependency parser, the phrase with butter should attach to spaghetti, and the phrase with chopsticks should attach to ate. And that is because we know that butter is a dairy product and it's some kind of food, so is spaghetti, but it's a pasta dish and so on. And chopsticks are tableware, and it's an article. We refer to this kind of knowledge as background knowledge. That's because this knowledge is not explicitly present in the utterances that are being encoded. It's based on some knowledge that we as humans share, and we just rely on that when we say things like this. On the other hand, say you're doing question answering on some sort of a structured context. So in this example, say you're doing question answering on tables, and you're trying to answer a question like how many medals did the 8th place finishers win based on this table. To get to the answer, which is 4, you'll have to first identify that the phrase 8th place finishers maps to these two rows in the table, and the word medals should map to this specific column given by total, and the answer can be arrived at by summing the two numbers given in the appropriate columns and rows. We refer to this kind of knowledge as contextual knowledge because while all the knowledge required for arriving at this answer is explicitly present there, we still need some extra knowledge to ground the question in the table and perform this reasoning. So clearly, these equations are overly simplistic, and we'll modify them into these two equations where at the first step, you're encoding the given utterances with additional knowledge, and in the second step, you're reasoning over the encoded representations using this additional contextual knowledge. Here are some of the publications that I was part of during my PhD that belong to these two general themes. I'll talk about these two papers closely during this talk, but I'll also briefly mention the work in the third paper there. So here's the outline. I'll first talk about incorporating ontology information into token representations, and then I'll talk about complex question answering and look at it as weakly supervised semantic parsing, and then I'll briefly talk about some potential next steps based on the stuff that I talk about in this presentation. The first work is joint work with Waleed, Chris, and Ed, and this is the outline of the first part. Okay. We are all aware, we are very familiar with word type embeddings, which are essentially word vectors, which are inputs to most natural language understanding systems. A key thing to note here is that most of these word vectors are often static and context free, and we have one representation per word type. What I mean by that is, say you have a word like pool, and you get one vector representation for that word, and the same vector representation is used in various sentences irrespective of the context that it occurs in. So for example, pool, the word vector representation is the same in both these sentences. She sat next to the pool table and she jumped into the pool. You clearly know that the word is being used in different senses here, but the same vector representation is used. And also, the vector representations do not explicitly encode this real world information that we are aware of, that a pool is some sort of a small lake. It's some sort of a body of water, and that it usually involves making an excavation to fill it with water and so on. So the solution we propose to address these shortcomings is to build ontology-aware token representations. By token representations, I mean context-sensitive vector representations, such that the word vector representation varies given the context. And we also ground them in ontologies. Particularly, we choose WordNet. The word vector representations are defined as expected values of the representations of WordNet synsets that they're linked to. This was a paper from last year's ACL, and it had similar motivations to the more recent Elmo embeddings. But the high-level difference there is whatever Elmo is doing with states from a deep language model, we are doing that using ontologies, explicit symbolic ontologies. So let's closely look at what the model is doing. Firstly, given a word like pool, we ground it in WordNet. We identify the various senses that WordNet gives us. For the word pool, WordNet identifies 9 different senses as a noun. And for each of those senses, WordNet also defines several hypernyms. That, for example, the swimming pool kind of pool is some sort of a pond. It's a small lake. It's a body of water, and so on. And the billiard sense of pool is some sort of a table game, which is an activity, and so on. So given this information, we can then represent this set of synsets and senses as some sort of a tensor, where one axis represents senses, the second axis represents hypernyms, and the third axis represents the embedding dimension. Then, when we want a word vector representation, we learn hypernym weights and SenseWeights so that we can compute dot products of these two weights with the given tensor to arrive at the word vector representation. In a traditional recurrent neural network encoder, you have one vector representation per word that is being fed into the recurrent unit. I'm showing an LSTM here, but it usually works the same with most recurrent units. You have one vector representation being plugged into each of the recurrent cells at any given time step. We replace that with the tensor, and we take the hidden representation for that time step that is being fed into the recurrent cell, and then compute a function on top of the hidden state and the synset representation to get back the word vector, which is fed into the given recurrent unit. Given that the final representation depends on the hidden state, this is context sensitive, and given that it depends also on this synset tensor, it is ontology grounded. Let us now closely look at what's happening within this red box where the function is computed. So we need to do two things. We need to compute the SenseWeights for the given tensor, and we also need to compute the hypernym weights. First, we define the SenseWeights as a probability distribution of the sense of the word given the word type. We parameterize that as an exponential distribution, and that is dependent on that is a function of the rank of the given sense given the word type as defined by WordNet, and the parameter is a rate parameter which defines how steep or flat the distribution is. The reason why we make it a function of the rank is because WordNet defines senses in descending order of frequency. That is, sense 1 is usually expected to be more frequent than sense 2 in some corpus. To capture this bias, we define this as an exponential distribution. And the parameter lambda, which is the rate parameter, is learned jointly with the encoder. So the model can decide how steep or how flat the distribution needs to be.
What are the word types?
The word types are the words themselves. So, yeah. So pool is the same word type, irrespective of the sense. So the hypernym weights are defined as a distribution of the hypernym given the syncset tensor in the context, and we define that as a multinomial distribution which is parameterized using a multilayer perceptron, which takes as inputs the slice of that is related to the hypernym in the syncset tensor and the hidden state. You may have noticed that this is very similar to how attention is computed in more recent encoder-decoder models. So you can think of this as the hidden state attending to different slices of the syncset tensor. Okay, so now that I've defined the model, let's look at some tasks. The task we'll look at is prepositional phrase attachment. When we are trying to apply this model to this task and any other natural language understanding tasks, it can be observed that the model that I've described can be plugged into any recurrent network neural encoder. And the parameters can be trained jointly with the encoder, the parameters being the syncset embedding, the sense priors, and the MLP parameters. So given that I've replaced the word vectors with syncset tensors, you may be thinking that I have added way too many parameters to the model. However, this is not the case because the same syncset representations are shared across several words. And in fact, even empirically, we notice that this representation does not cause parameter space explosion. So the plot shown here on the right is a sample of 50,000 sentences taken from a section of gigaword. And as you keep increasing the number of sentences, you see how the space of word types and syncset types changes. The red line shows the syncset types and the blue line shows the word types. And as you can see, at around 35,000 sentences, the number of word types increases more. I mean, it goes above the syncset types. So yeah, now looking closely at the specific task we're interested in, prepositional phrase attachment. The problem here, as I have described earlier, is given a sentence with some prepositional phrase, we need to find the candidate head words the prepositional phrase attaches to. So again, looking at the same example that I've shown before, in the first case, she ate spaghetti with butter. Given that sentence, we need to identify spaghetti as the head word for the prepositional phrase with butter. And similarly, in the second sentence, we need to identify ate as the head word. The training data set comes from Wall Street Journal. It's a set of 34,000 sentences in train and about 2,000 sentences in test. The model itself is a bidirectional LSTM for the encoder and an MLP for doing the prediction. And we are just predicting the probability of the head word given these inputs. Here are some results of the model. Firstly, a simple baseline is to always attach to the closest head word, and that itself is a very strong baseline because it is English, which gets about 82% accuracy. The first point of comparison here is whether doing syncset embedding helps. The two red boxes shown here are systems where you're on the right, you're embedding synsets, some variants of the model that I just described, and on the left, you have models where you don't have a syncset embedding. As you can see, in general, embedding syncset helps. The two systems that are shown here on the left, where there is no syncset embedding, of those, the first one is a simple LSTM model, which uses the same architecture that I showed before, but instead of the ontology-aware embeddings, we are just using glove vectors. And the second system that I have shown, it gets a slight improvement on top of the first system, and it uses retrofitted vectors from Manal Faruqi's work from a couple of years ago. Those vectors also use WordNet information, but they use WordNet information to get better type embeddings. So they still have static representations and not dynamic ones like the ones I just showed. The second point of comparison is whether context sensitivity helps. To do that, we define a context agnostic variant of the model that I just showed, where we just replace the attention with a uniform distribution. And as you can see, context sensitivity helps very much. There is a significant improvement of close to 2 percentage points by adding context sensitivity. The third point of comparison is whether sense order bias, the exponential distribution I talked about earlier, whether using that helps. And you can see that that indeed helps. And we do that by replacing the exponential distribution with the uniform distribution. And and one important observation here, at least for me, is that even without using the exponential sense bias that I showed you earlier, we still get a decent performance, outperforming the other models that I showed here, which is important because not all ontologies come with the sense order that WordNet gives us. So in cases when you're building this model for other ontologies, you can simply replace the exponential distribution with a uniform distribution and still get a good model. Here are some results showing the effect of training data size with the model. What I've shown here is how the test accuracy changes when the amount of training data varies for both the ontology-aware model and the simple LSTM. A key observation here is that even with 5,000 sentences in the training data set here, the ontology-aware model does better than the simpler LSTM model with the whole data set here. So, which is a very important observation because the onto-LSTM model is being trained with about a seventh of the training data set. So, especially in low data settings, when you're training a model to do some semantic tasks, this kind of a model could be very useful.
What happens as you tail off further? 5,000 seems like quite a high benchmark.
You mean even further to the left?
Yes.
I don't have those results, but it'll be interesting to see. Yeah. And even with adding more data, the onto LSTM model keeps getting better. Here is some qualitative analysis showing what exactly the ontology-aware model is learning. The blue bars are attention being given to each of the synsets for the given word. So in both these examples, the LSTM model makes an incorrect prediction and the onto LSTM model makes the correct prediction. So if you look at the first sentence, it says local competitors have had phenomenal success with concentrated soap suds. The reason why the LSTM model doesn't get it right is because soap suds is an infrequent word. In fact, it never occurs in the training data set. It occurs only once in the test set. But still, the onto LSTM model was able to leverage the information that soap suds is a kind of foam, it's a kind of bubble, and it's a kind of a ball of some sort. And by placing attention on all of these and placing zero attention on the more specific concept, it was still able to get the right prediction. In the second example, which says there has been little news to account for such buoyancy in the oil markets, even here the LSTM model gets it incorrect and the onto LSTM model gets it right. What's interesting in this example is that the word buoyancy is being used in a metaphorical sense in this sentence. And in fact, WordNet doesn't account for this specific sense of buoyancy. Even then, the onto LSTM model was able to place some attention on various different senses. These are synsets coming from different senses, and the attention is kind of distributed across them, and it was still able to make the right prediction. Okay, to summarize this part of my talk, I described a method to incorporate explicit background knowledge into NLU systems. We used WordNet here, but it can extend to other kinds of knowledge bases as well. And I've shown empirically that external knowledge is way more useful in low data settings. Before I move on to the next part of my talk, are there any questions? Yeah.
So I guess one little question about this PP attachment task is how well do state-of-the-art parsers do on PP I sort of thought PP attachment was like more or less
A solved problem.
not the hard part of parsing anymore. Is there any reason to think that it is?
Actually, there is, even with, I have a slide that shows, yeah. Here are some dependency parsers on the same,
Okay, this is good.
yeah.
So you're doing better than,
So these are some dependency parsers. The compositional parser is from the recursive neural network model from Richard Zucker. And yeah, so these are task-specific classifiers. So yeah, we are doing better than most dependency parsers. And in general, I think we've observed that prepositional phrase attachment is one of those bottleneck tasks in dependency parsing because it requires a lot of semantics being modeled.
that has been said, yeah.
There was another question.
Can you combine this approach into, say, dependency parser and get the same or even better results?
Yes, actually, I didn't show those results here, but they're in the paper. We show that we get much higher accuracies when we actually put them in the dependency parser. I can maybe talk more about it offline. Okay. All right. So moving on to the second part of my talk, I'll talk about complex question answering, and I'll look at it as a weakly supervised semantic parsing problem. This is joint work with Matt, Luke, and Ed. And yeah, this is the outline of this talk. First, let us look at what exactly the task is. So what I mean by complex question answering is that if you are given some sort of a structured context, like a table, and you're asking a question like which athlete was from South Korea after the year 2010 based on this table. And to arrive at the correct answer, Kim Yoon-na, you'll have to perform the following reasoning steps. First, you need to get the rows where the nation column contains South Korea. You have 2 of them here. And then you have to filter the rows where the Olympics has a value greater than 2010, which filters it down to just this one row. And then you need to get a value from the athlete column from the filtered rows. And you'll get the correct answer by doing that. This reasoning can be succinctly described in this program, where using some sort of a formal representation. What this is doing is that it is first identifying these two constraints, that the nation needs to be South Korea and the year needs to be greater than 2010. And you take an intersection of the rows given by each of these constraints, and then you get the athlete column out of it. Similarly, when you're doing question answering over figures, this is an example from the Cornell Natural Language Visual Reasoning dataset. When you're doing question answering on this, or in fact, when you're evaluating whether a given statement is true or false in this, you have a statement like there is exactly one square touching the bottom of a box, which is true in this case because that's just this one square. To evaluate whether that statement is true or false here, you need to perform the following reasoning steps. You need to get all the objects touching the bottom of a box and then filter squares from it and then count the number of objects which come from the filtering step. And you return true only if the count is 1. This can be described in this program here, which is again using a similar formal semantic representation that I described before. And the task is set up such that you don't have the logical forms for training a semantic parser. You just have the questions, the answers, and the worlds in which the statements or the questions need to be evaluated in. What I mean by worlds is the context. So in the first case, in the Wikitable questions dataset example, the world representation is the table. And in the second example, the world representation is a figure. Now, when you train a semantic parser, a question answering system that uses semantic parsing on a data set with the triples, which are the utterances, the worlds, the context representations, and the answers, at test time, given a new utterance and a world, you need to find the logical form which evaluates to the correct answer when evaluated in the world. That comes with the utterance. So as you can see, this is a weakly supervised semantic parsing setup, and that's what I'm going to talk about now. So let's look at why this is a hard problem. The biggest challenge when you're doing weakly supervised semantic parsing is having to deal with spurious logical forms. So what I mean by that is the following. Again, using the same example that I showed before, you have the answer, Kim Yuna, and you're trying to, because you're building a semantic parser, you need to map the utterances to logical forms, and you're trying to get the logical forms which evaluate to the correct answer. When you do that, you will end up getting lots of different logical forms. Only a few of them will be correct. So for example, these are 4 of the many logical forms that give the correct answer. Let's look at what they mean. The first one says athlete from South Korea after 2010, which is correct. And the second one says athlete from South Korea with 2 medals, which also gives the correct answer. The third one says first athlete in the table with 2 medals, which also gives the correct answer. And the fourth one says athlete in row 4, which is also the right answer. So you're trying to build a semantic parser using noisy data like this. So that is challenging. Even in the second example, when you have there is exactly 1 square touching the bottom of a box, these are some of the logical forms that evaluate to true. Yeah. Oh, these all the ones in red are spurious.
Why exactly?
Because they are giving the right answer, but not for the right reasons.
But this is a weakly supervised task. Why do you care about whether they give the correct answer or not? It seems like you only care about if they give the correct answer.
That's a good point, but when we're building a parser, we need some information that could generalize across questions, right? So if you learn a mapping from the utterance to one of these spurious logical forms, and you get a new utterance, you can't really map that information. That's one way of defining it, yeah. So yeah, even in this example, you have several logical forms which give the right answer. These are what they mean. Again, the first one is the correct one, but the other ones are increasingly simpler. So the second one says count of the yellow squares is 1, which is true, and so on. And the extreme case is that it says that there exists an object, which is true. And so as you can see, in this case, the problem of spuriousness is even more serious because the answers are binary. And in fact, when you sample random logical forms, they have a 50% chance of giving the right answer, but only a few of them are actually correct. So here are some approaches for dealing with spuriousness that I'll talk about in this presentation. First, I'll talk about using lexical cues from a minimal lexicon to deal with the binary supervision, which is specific to the NLVR example that I just mentioned. And I'll show some results on NLVR using that approach. Second, I'll talk about a novel training scheme to gradually increase the complexity of logical forms. We will rely heavily on the compositionality of the target logical form language, and I'll show results on the NLVR dataset and the Wikitable questions dataset using that approach. These are methods and results that are currently in submission in this paper. Okay. So before I talk about the approaches for dealing with spuriousness, let me mention how we train a semantic parser using this, and I'll talk about constrain decoding particularly and how it's useful for training semantic parsers. We use expected risk minimization to train semantic parsers here. We define some cost function, which is dependent on a couple of different factors, which I'll talk about in a few minutes. But given some cost function, we are trying to minimize the expected value of that cost under this probability distribution, which is the probability of the logical forms given the utterances. And we want to minimize that cost over the entire data set. Now let us look at how we can estimate the probability distribution of the logical forms given the utterances. Doing that requires enumerating valid logical forms. Since we are using an encoder-decoder model, the decoded sequences are not always guaranteed to be valid logical forms. That's because the decoders are usually some sort of recurrent neural networks, and if they produce one token at a time, we can't be sure whether the produced sequences have things like matching parentheses and whether the methods respect the type constraints of the functions and whether they take the right arguments and all those things. So the problem here is how we ensure validity of the decoded sequences, and to do that we set grammar constraints on the output space of the decoder, and that's what I meant by constraint decoding. And this is work from last year's EMNLP paper. I won't go into the details of this paper, but I'll briefly mention how we are doing constraint decoding here. So given a logical form sequence, given a logical form like the one that I just showed here, we want to produce a tree. We want to decode the logical form that I've shown here as a tree, and each non-terminal in this tree is a type of the subtree under it. I'm using a formal semantics notation here using the angular brackets. Again, the details are not very important, but the idea here is that every non-terminal can be thought of as a function which takes an argument which is the first symbol and returns a different kind of argument. Each of these elements is typed, and it can also be a basic type, which is again also typed. So given these types, we can generate a whole type tree as a logical form. Again, because we are using a decoder, we are trying to generate the whole tree as a sequence of typed actions. Let's see how that goes. Say we are trying to parse this sentence. This is how constraint decoding grammar constraint decoding would work. What I've shown here on the left is a sequence of generated actions, and what I've shown here on the right is a partially formed logical form. And this is a non-terminal stack which keeps track of the non-terminals that still need to be expanded. First, we generate this action start gives C. C here is a cell type from the table, which is correct because the question is actually asking to retrieve a specific cell from the table. And the second action we produce is an application of a function on a basic type, which is a row. And once that is done, the non-terminal stack is popped, and the top of the non-terminal stack is popped, and it now has two different non-terminals which still need to be expanded. And as we keep going, we have a series of applications and some terminals being generated. When that happens, as you can see at each step, when a function application is generated, we can also trivially put matching parentheses in the logical form. Because it's straightforward. When you're actually applying a function, the Lisp flex string contains this matching parentheses, and so on. So once we have all the generated actions, the non-terminal stack is empty. We have the complete logical form present. And because of the productions being typed, we don't have to worry about mismatched types in function applications. So as you can see, the trees are guaranteed to be syntactically and semantically valid. That's because you, say for example, you have something like nation, and that needs to apply on a type of a cell because nation has cell as the argument. It cannot take a number, so you wouldn't have a semantically invalid logical form where a function is taking an invalid argument. Does that make sense?
I guess I'm not confused between the difference. Your definition of syntactically and semantically valid in this case.
Syntactic validity is producing a tree,
yeah.
Right? You can still produce a tree where the functions can take invalid arguments. That would be syntactically valid but semantically invalid.
Sure.
Does it make sense?
Yeah.
Okay. Right. So let's now that I've described how we are training the system, let us see how. Let us look at the first solution for spuriousness that I mentioned before. The first one is coverage-guided search. The insight here is that if you're mapping a sentence like this, there is exactly one square touching the bottom of a box, to a logical form like the one that I've shown before, there is a significant amount of trivial overlap between the words in the utterance and the functions and the entities in the logical form. We can actually leverage that, and we can use the overlap as a measure to guide search, and that is the key insight behind coverage guidance. The way we do that is we first define a lexicon, which is domain specific, but for the case of NLVR, we didn't have to define a huge lexicon. In fact, what I've shown here is the entire lexicon that we're using for NLVR. It's less than 40 rules. So given that lexicon, there are some target symbols that are triggered from the given utterance. So for the utterance that I've shown here, say it triggers count equals 1 square and touch bottom. We define then a coverage cost, that is the number of triggered symbols that do not appear in the target logical form, or in the logical form, in a candidate logical form that is being produced. So a concrete example, say you have the decoder producing each of these logical forms. These are candidate ones which need to be ranked. And you have these target symbols that are triggered. Then the first logical form, which is the correct logical form, has a coverage cost of 0 because it has all 4 of the triggered symbols. The second one has a cost of 1 because it doesn't have touch bottom, which is one of the triggered symbols, and it doesn't occur here. And the last one, which is one of the logical forms we want to avoid, has a coverage cost of 4 because it has none of the symbols that are triggered. All right. So going back to the expected risk minimization objective, we now define the cost function as a linear combination of the coverage cost and the denotation cost. What I mean by the denotation cost is whether the given logical form evaluates to the correct answer or not. When we have the cost defined like this, we have some sort of a bias coming from the coverage as well, and that ensures that the logical form is relevant to that given utterance. Now I'll talk about experiments using coverage-guided training. I'll talk about 2 different settings. The first is when we are training a coverage-guided semantic parser from scratch, where we are using constrain decoding during training to search for valid logical forms that minimize the cost that I just talked about. One consideration there is that we are actually searching during training, so the online search may be expensive. To see how that affects the parser, we also train a different variant where we use again the coverage cost to do some sort of an offline search exhaustively till a bounded length, and use those to initialize the parser, the online search parser. And a consideration there is that given that it's offline search and we don't really have a beam to sort these the candidate logical forms being explored, we can only do this till a limited depth. So yeah, so here are the results of using coverage-guided training on NLVR, and the results are using the structured representations that come with the dataset if you're familiar with it. What that means is that we are not directly looking at the images, but JSON representations of these images, and we're thinking of this as purely a semantic parsing task, not really an object recognition task. Okay. What I've shown here on the left is the setting where you're training the parser from scratch. As you can see here, when you don't have any coverage at all, the accuracy is 56.4%, which is only slightly better than random, and in fact it is similar to predicting just the majority class. So you can safely say that when there is no coverage and when you're trying to train a semantic parser, it just doesn't turn anything. But once you add coverage, you get this significant boost of close to 20 percentage points, which is great. It shows that coverage-guided search generally works. So the second setting here is when the model is initialized from an maximum marginal likelihood, which is trained on the seed set of logical forms, which are given by the offline search model. And when you do that, it generally does much better when there is no coverage than when it's trained from scratch. But note here that even the offline search logical forms still use coverage. So a lot of this is maybe also due to coverage. And even when you add coverage on top of it during the online search model, we still get close to 3 percentage points improvement. So just by using coverage and this simple initialization trick that I just described, we were able to go from close to random performance to 80.7% on this task of NLVR. Yeah. Yeah.
So those numbers you just showed, those were just on the kind of, did I get the right true false answer? Is that correct?
Yes, that's correct.
Do you have any sense on, was it getting it for the right reasons or not?
Yeah, so There is another metric for dealing that's kind of a proxy for what you're saying. It's consistency. What that means is that the NLVR dataset is organized such that the same sentence occurs with different figures. So we can check in how many cases the sentence is giving the right answer in all those cases. So yeah. In that case, the comparable number to this model is close to 63%, 60 to 63%. So yeah. Right. So that's the first technique for dealing with spuriousness. Now I'll talk about the second technique, which is iterative search and maximization. Based on the results that I've just shown, the observation so far is that coverage guidance generally helps a lot. And also initializing the coverage guided training with offline search helps even more. So based on this, a natural question is that given that the model used for the initialization is limited by doing exhaustive search, which can be done only till a bounded length, can we actually do better? And can we actually get a better set of logical forms to initialize the model that we're actually training? And yeah, we can actually do that. We can use a learned model instead of doing exhaustive search. And that is the key insight behind defining this iterative search and maximization technique. So what we actually do here is we use this algorithm where in the first step we get a seed set of logical forms through heuristic search, like I just mentioned before, till some bounded depth k. Essentially, this k is the depth that your CPU allows you. Essentially, you can max out on your CPU cycles and go till the max depth and get whatever logical forms you get. And then you train an MML model, which is essentially a maximum marginal likelihood model using those logical forms. And then we use that trained model to initialize the expected risk minimization model that I just described. And we train the ERM model till some depth which is greater than k. Because you're using beam search in online search here, we can actually go to a greater depth. And so with some sort of a step size. And then we can use the trained ERM model to decode and obtain logical forms. And this set of logical forms that are obtained after doing this is expected to be a larger set than the ones you started out with. And then you reset the value of k to be k plus s, and then go back to step 2. You can essentially keep on doing this. You can keep on getting logical forms, using that to initialize the ERM model, get more logical forms, and go back. You can keep on doing this until your accuracy on your dev set stops increasing. And that, in fact, helps. These are the numbers coming from various iterations of doing iterative search on the NLVR dataset. This iteration 0 here is using the seed set of logical forms. And I've shown here, what I've shown here are the accuracies from the MML model, or the offline search model, and the ERM model, which is the online search model. And as you can see, both the numbers keep on increasing until iteration 4. And I've also shown the training set coverage, which means the number of utterances for which you can get logical forms which also respect the coverage constraint. So we start out with close to 50% of the training set for which you can actually get valid logical forms. And we go up till 75% on iteration 4. So the best accuracy we can get on the dev set for this task is 85.4%. And we observe the same trend for the Wikitable questions dataset as well. And after 2 iterations, the dev accuracy stops improving. But yeah, we can go from a 35.4% accuracy, which is obtained from training an MML model on some set of logical forms obtained from dynamic programming or denotations and algorithm that we used before. I didn't go into the details yet, but yeah, we go from a 35.4% accuracy all the way till 41.3%, which is a significant improvement on this data set. Here are some logical forms that we obtain for NLVR as we keep on increasing the complexity over iterations as we keep on increasing the value of k or the max depth until which we search. First, when we search exhaustively, we can only get logical forms for utterances like this, the one that I've shown at the top. There's a tower with 4 blocks, which is fairly simple. But as we keep on increasing, as you can see, the complexity of the logical forms increases as well. And the kind of semantics we can express keeps getting complex. And for example, here you have things like there is a yellow block on top of a tower with exactly 3 blocks, which involves significant nesting and so on. Okay, to summarize, I talked about complex question answering, and I looked at it as a weakly supervised semantic parsing problem. And I noted that it's desirable to constrain the output space when you're training a seek-to-seek model for semantic parsing. And when you're doing weakly supervised semantic parsing, you have to deal with spurious logical forms, and I've described 2 techniques to deal with that. I talked about coverage for semantic parsing using minimal lexicons, and I also talked about an iterative search technique that alternates between exploring new paths and maximizing the likelihood of found ones. And I showed improvements on both wiki table questions and NLVR. Okay, before I move on to the next part of the final part of my talk, are there any questions? Yeah.
Just wondering about the consistency numbers for the iterative MML.
Right.
Does that actually improve consistency as well?
Yeah, it does improve consistency as well.
I have a question on the logical forms. So I see some of the predicates where, box exists, object exists. So if you are creating predicates like that, which takes into account what types of figures are there. So if a new figure being added, you have to train again. Like if you have box exists and if it takes in triangle, and then you add a hexagon which is not there. So
yeah, so the logical form language, as I described, is domain specific, and we assume that there are only so many objects. But in a situation where you are adding new shapes to the domain, then I guess if you parameterize it correctly, if you can somehow parameterize a mapping between the given phrase and the new function that you're adding in terms of your coverage lexicon, I think it should be straightforward to do that. Yeah, we've not experimented with that setting, but I think it should be doable.
Question?
Yeah.
I'm wondering about the interplay between the 3 of the things that you mentioned. Constraint decoding seems to be important while you're doing the iterative search.
Right.
So after you finish training, do you still need to do the iterative search, or do you stop using that? You only need it for training, and then you only use the constraint decoding while you're actually decoding after.
Yeah, we only use constraint decoding while we're actually decoding.
So the difference between offline and online is only relevant for the training.
That is true. Yeah.
And the first solution for the spuriousness is like orthogonal to the second, right? So do you use it while you're doing the experiments here? Or?
Yes. So the iterative search for NLVR uses coverage, which is the first solution, because coverage is important for dealing with binary supervision. But for the wiki tables results, we don't use coverage for iterative search.
Why don't you use coverage for wiki tables?
Because we start out with a good set of logical forms, which are given to us by the dynamic programming on denotations algorithm, the DPD algorithm. And once we do, because it already provides strong lexical cues, we found coverage to be unnecessary.
So is the iterative search orthogonal to approaches which use dynamic programming of denotations?
Yes, it is.
And you could improve your initial heuristic search using.
That is true. Yeah.
And are those complementary, or are they like why should I think that they're complementary?
So you're talking about the kinds of logical forms you get when you're using a trained model. How is that complementary to the original set of logical forms?
If I were training my own semantic parser and I had to choose between using logical forms I extract via dynamic programming of denotations or using this iterative search, or both, why why should I expect that using both would be an improvement?
So yeah, a couple of things. Firstly, DPD uses some sort of heuristics. It also uses um, um, several techniques for addressing spuriousness, like defining fictitious tables where you randomize the order of rows and stuff and use those to prune the initial set of logical forms, so they are expected to be more precise. The other thing is that DPD doesn't involve any learning. So when you are actually using online search or learning to search in the case that I just talked about, you can actually, it's possible that as you go on, you can learn more and use that information to get better logical forms. And we actually observed that the set of logical forms keeps on increasing. Even when we start out with DPD, we can get more logical forms which are, evaluate to the right answer. Is there? Yeah.
And so the reason you didn't have constraints for the other data set, is it because the lexicon would have been very long?
That is, so yeah, that's not exactly the reason, because we could have still defined the lexicon for the easy mappings, like things like sum or count or min or max or things like that, and we could have still gone with that. But we just didn't find it necessary. In fact, we did define such a minimal lexicon, and we observed that it really didn't help the performance, or it didn't add anything, because we are already starting out with a strong set of logical forms which provide enough lexical use.
So that problem is harder, right? How come you started with a bigger set for those ones?
Because so there are actually two things. That problem is harder in that it is more open domain, but it's also easier because the denotations are not binary. So you can more easily get logical forms which give the right answer, or they're expected to be less spurious that way.
Defining the lexicon, the one you used to map predicates to strings, if they are like similar because they use the same characters or same words, why don't you try to use an attention alignment kind of thing instead of manually defining? So
yes, that could be done. However, starting out from scratch, we are actually using attention in our encoder decoder model, and we see that when we train it from scratch without using the lexicon, it doesn't learn anything, and that's because you don't have any guidance as to what the mapping should be. It can learn to map to random things over a set of noisy logical forms. So because of that, it's very hard to rely on attention to learn a mapping. Does that make sense? Okay, moving on to the third part of my talk. I'll briefly talk about some potential next steps that I've been thinking of based on the problems that I just talked about. Firstly, I talked about complex question answering over structured contexts, but we can extend this to unstructured context as well, and it would be great if we can somehow transform structured context into graphs and do some sort of complex question answering on top of them. Here's one reason why that is important. This is a screenshot of the demo from Allen NLP using the BiDAF model on the squad dataset, which is a reading comprehension dataset, and this is one of the examples where you have a passage about the movie The Matrix, and you're asking a question, who stars in The Matrix? And it gives you the right answer. It selects the span, which identifies the actors in the movie. However, if you asked how many actors starred in The Matrix, it is, well, out of scope for BiDAF because it's a span selector, but in spite of that, it's important to observe that things like this cannot be handled by the current reading comprehension systems we have. It simply identifies 1999, and that's probably because it identifies that how many should map to a number, and that's the only number in this paragraph. So to deal with problems like this, it would be great if we can define some sort of symbolic reasoning operations on top of paragraphs to deal with questions like this. One way we can do that is to transform the paragraph into a graph structure and graph representation. We can parse sentences using into predicate augment structures or discourse structures defined by the paragraph, and we can maybe perform operations like selecting the argument of the starring relation, where one of the arguments is the matrix, get the span that is identified, split its entities, and then perform a count operation to answer the question like how many actors start in the matrix. So yeah, that would be great if we can do that. And some of the considerations here are how do we get the structure out of the text, and how do we define operations that are sufficiently general for querying. And it would be great if we can train both the querying part of the system and also the paragraph parsing part of the system jointly. These are things that have not been done before, but it would be great if that line of research can be explored. Another line of thought is doing general structured prediction using weak supervision. I talked about weakly supervised semantic parsing, but we can think of weakly supervised variants of other kinds of structured prediction problems as well. For example, if you're building dialogue systems, goal-oriented dialogue systems, you can get supervision in the form of whether the goal is achieved or not. There is some work happening in this, but some of the techniques I talked about may be applicable there as well. Or say if you're transforming natural language into API calls over some well-defined API, and you have supervision only in the form of the execution being correct or not, we can do weakly supervised transformations of natural language to API calls or train a system using weak supervision even in that case. There is some work in that using natural language to SQL, but it can be done with arbitrary APIs as well. Also, if you're doing machine translation and all the input you're getting, all the feedback you're getting is whether the user is satisfied with the translation or not, how do we train a system using it? So these are some of the things that could be explored. All right. To summarize, I described knowledge-aware natural language understanding and made an argument that knowledge inputs help build better NLU systems. In the first part of my talk, I talked about better encoding using ontological information from WordNet, and I showed that it helps a lot more in low data settings. In the second part of my talk, I described reasoning with grammar constraints, coverage, and iterative search. And I showed that using this additional contextual knowledge for this task lets the reasoning module focus on more important aspects of semantics instead of focusing on trivial aspects like matching parentheses or augment type accuracy and things like that. We already have powerful models. I think it would be great if we can use that for learning something that's more important than those things. Thank you.